Mastering algorithm efficiency. Advanced measurement techniques and optimization strategies. Algorithm efficiency is the cornerstone of high-performance computing, determining whether a program runs in seconds or years. For developers and researchers on platforms like Algohay, mastering this concept means understanding both theoretical analysis and practical implementation nuances. In today's era of big data and complex systems, even minor inefficiencies can escalate into significant bottlenecks. This article dives deep into measurement methodologies, optimization strategies, and case studies to equip professionals with actionable knowledge. Understanding time complexity analysis. Time complexity quantifies the computational effort required by an algorithm relative to the input size. It is typically expressed using Big O notation, which abstracts away constant factors and lower-order terms. This abstraction allows programmers to compare algorithms independently of hardware specifics. However, it also introduces challenges. For instance, Big O hides constants that may dominate small inputs but become negligible for larger ones. Dominant terms. When analyzing expressions like O, n superscript 2 plus n, the quadratic term dominates for sufficiently large n, simplifying comparisons between algorithms. Practical implications. An O(n) algorithm will outperform an O(n log n) approach only after a certain threshold of input size, depending on hidden constants. Understanding asymptotic behavior requires recognizing that Big O describes growth rates, not absolute runtimes. A linear time solution might still be slower than a logarithmic one for modest input sizes due to higher coefficients. Real-world applications often involve mixed time complexities. For example, a nested loop may have a worst-case O(n superscript 2) runtime, but average-case performance depends heavily on data distribution patterns. Space complexity considerations. While time complexity focuses on computation steps, space complexity measures the memory footprint during execution. Both are critical dimensions in evaluating algorithm efficiency. Memory constraints often drive design decisions, especially in embedded systems or environments with limited resources. An algorithm with superior time complexity may be impractical if its space requirements exceed available capacity. For example, recursive implementations frequently consume stack memory proportional to the recursion depth, whereas iterative counterparts typically use fixed amounts of memory. Trade-offs exist between time and space. Hash table lookups achieve O(1) time complexity at the cost of increased memory consumption compared to binary search over sorted arrays. The memory time trade-off principle. Modern algorithms often exploit this principle intentionally. Bloom filters reduce lookup times through probabilistic guarantees, accepting false positives in exchange for minimal storage costs. Data compression techniques similarly balance speed against memory savings, encoding information redundantly to enable faster access while reducing overall storage demands. Caching mechanisms represent another manifestation of this trade-off, storing intermediate results in fast access memory to avoid recomputation penalties later in the workflow. Empirical benchmarking versus theoretical analysis. Theory provides foundational insights, but real-world performance hinges on numerous variables including hardware architecture, compiler optimizations, and operating system scheduling policies. Benchmarking involves executing code across different input sizes and measuring actual runtime durations. While invaluable for identifying practical issues, this method lacks generalizability across diverse hardware configurations. Microbenchmarks isolate specific components, enabling precise evaluation of individual functions or operations. Yet they risk misleading conclusions if external factors like caching effects are not carefully controlled. A robust approach combines theoretical predictions with empirical validation. For instance, confirming that a theoretically optimal O log n algorithm performs better than an expected O(n) alternative on measured datasets ensures confidence in theoretical claims. Profiling tools for performance tuning. Performance analyzers provide granular insights into execution timelines, helping identify hotspots requiring optimization. Tools like Prof for C/C++ or JProfiler for Java offer detailed call graphs and timing breakdowns. Instrumentation-based profilers insert monitoring code automatically, collecting statistical data without manual modifications. These tools excel at detecting inefficient loops or excessive function calls. Sampling profilers operate differently by periodically interrupting execution to capture stack traces, providing less precision but significantly reduced runtime overhead. Selecting appropriate tooling depends on project requirements. Debugging simple scripts may require lightweight solutions, while optimizing high-throughput services necessitates advanced instrumentation capabilities. Design patterns for efficient code. Certain architectural choices inherently influence efficiency. Divide and conquer strategies decompose problems into smaller subproblems, improving manageability while preserving tractable complexity bounds. Greedy algorithms make locally optimal choices iteratively, producing globally optimal solutions for many classic problems like minimum spanning tree construction or shortest path finding. Dynamic programming stores previously computed states to avoid redundant calculations, transforming exponential time algorithms into polynomial ones through memoization techniques. These paradigms represent fundamental building blocks rather than isolated tricks. Combining multiple patterns often yields breakthrough efficiencies unattainable through singular approaches alone. Evaluating parallel algorithm efficiency with modern multi-core architectures becoming standard, assessing parallel algorithm efficiency presents new challenges. Speed-up measurements must account for both improved throughput and additional coordination overhead. Andel's law calculates theoretical maximum speedups achievable through parallelism, revealing diminishing returns as non-parallelizable portions grow relatively larger in proportion. Load balancing becomes crucial in distributed systems, ensuring workloads remain evenly distributed among processing units to prevent bottleneck formation. Communication overhead represents a critical consideration, particularly in distributed environments where network latency can negate gains from added compute resources. Weak scaling versus strong scaling metrics. Weak scaling evaluates how well algorithms scale as both workload and number of processors increase proportionally. Ideal weak scaling maintains consistent runtime despite growing problem sizes. Strong scaling examines how performance improves with increasing processor counts for a fixed problem size. Perfect strong scaling achieves constant runtime regardless of cores used. Both metrics reveal strengths and weaknesses in parallel designs. Hybrid approaches combining shared memory and distributed memory models often yield the best scalability characteristics. Compiler optimizations and their impact. Modern compilers apply various transformations that can dramatically affect algorithm efficiency without programmer intervention. Constant folding, dead code elimination, and instruction reordering are routine optimizations. Loop unrolling increases cache utilization by processing multiple iterations simultaneously, though it trades memory usage for reduced branch prediction overhead. Predictive prefetching enables CPUs to load anticipated memory locations before they're accessed explicitly, minimizing stalls caused by slow memory access speeds. However, relying too heavily on compiler magic risks creating fragile codebases that behave unpredictably across different compilation settings or target platforms. Hardware-aware algorithm design. Efficient algorithms consider underlying hardware characteristics, exploiting cache hierarchies, vector instructions, and memory bandwidth limitations strategically. Cache-oblivious algorithms perform optimally across varying levels of memory hierarchy without explicit parameter tuning, making them particularly attractive for portability reasons. SIMD, single instruction multiple data, extensions allow parallel processing of data vectors through specialized CPU registers, achieving substantial speedups for numerical computations. Floating point arithmetic introduces additional considerations, with rounding errors potentially accumulating in ways that undermine algorithm stability unless carefully managed through error analysis techniques. Measuring real-world algorithm efficiency. Theoretical analysis remains essential, but practical deployment reveals unexpected interactions between algorithms and production environments. Latency spikes from disk I/O or contention for shared resources can swamp otherwise efficient code. Monitoring infrastructure offers visibility into actual performance profiles, tracking metrics like request rate, response time percentiles, and resource utilization across different traffic loads. Anomaly detection systems flag unusual degradation patterns early, alerting engineers to potential issues before they cause service disruptions or degrade user experience. Chaos engineering principles push systems toward edge conditions deliberately, uncovering rare failure modes that static testing would miss while strengthening resilience against unpredictable variations. Comparative studies across problem domains, different application areas impose distinct efficiency constraints. Search engines prioritize query processing latencies, while scientific simulations focus more on energy efficiency metrics. Machine learning pipelines face unique trade-offs between training duration and inference speed, influencing model selection and hyperparameter tuning strategies. Blockchain protocols must balance consensus verification speed with security guarantees, demonstrating how domain-specific requirements shape efficiency criteria. These domain differences highlight the necessity of context-aware optimization. What constitutes excellent performance in database indexing may prove entirely unsuitable for real-time video rendering tasks. Trends in modern algorithmic research. Ongoing research continues pushing boundaries in algorithm efficiency, exploring novel mathematical frameworks and hybrid approaches. Approximate computing leverages intentional imprecision to achieve dramatic power savings. Quantum algorithms promise revolutionary improvements for select problem classes, though current hardware limitations restrict immediate applicability primarily to laboratory experiments. Neural networks inspire new perspectives on algorithmic efficiency, suggesting that biological-inspired approaches might eventually surpass traditional computational models in certain domains. Advances in algorithmic game theory are reshaping our understanding of decentralized optimization, offering fresh insights into designing efficient mechanisms for distributed decision-making processes. Education and skill development pathways. Building proficiency in algorithm efficiency requires structured learning journeys encompassing both theoretical foundations and hands-on experimentation. Online courses and interactive platforms provide accessible pathways for skill acquisition. Hands-on coding exercises reinforce conceptual understandings, allowing learners to observe firsthand how different implementations affect performance outcomes in concrete scenarios. Engaging with communities like Algohay facilitates peer review and mentorship opportunities, accelerating knowledge transfer and fostering collaborative innovation. Continuous learning remains vital given the field's rapid evolution. Staying updated with academic publications, industry reports, and open-source contributions ensures practitioners remain competitive in their professional pursuits. Conclusion. Algorithm efficiency encompasses a vast spectrum of considerations, from foundational theoretical analyses to cutting-edge research frontiers. Understanding these multifaceted dimensions empowers developers to build smarter, faster, and more scalable solutions. To thrive in the ever-evolving landscape of algorithmic design, embrace a mindset of perpetual curiosity and experimentation. Leverage the wealth of resources available on platforms like Algohay to continuously refine your skills and contribute meaningfully to the advancement of computational science.